Hello, so this is the first type of the biomolecules, okay, carbohydrate. The carbohydrates can be divided into several categories. Let's start with the monosaccharide. Monosaccharide is a smallest building block of the carbohydrate. So after then, the monosaccharides may condense together, creating higher order of the saccharides unit, like disaccharide. So you may heard about the name of monosaccharide like glucose, and you know that two of the glucose unit can condense and you produce the maltose as a product. But not only the maltose, in a way that glucose condensed together, you can also prepare or produce other disaccharides molecules as well. It depends on how they connect to each other. Okay, that I will talk about it later. Apart from disaccharide, we can create in higher order, as I said, of the carbohydrates, like trisaccharides with 3 subunits of the monosaccharides, or tetrasaccharide, or higher than that. So with higher numbers of monosaccharides connected, we call them together as oligosaccharides, okay, roughly. And if we have a very long polymer chain of the carbohydrates, we call them as the polysaccharide. So what difference between this oligosaccharide and polysaccharides? Oligosaccharide, because we know that this is a kind of polymer, okay? And monosaccharides condense together, creating polysaccharide. It can be very, very huge molecules, starting from maybe can be higher, up to several thousand units of the glucose or several thousand units of monosaccharides. So if we have just some very small chain, like 5, 10, 6 monosaccharides, we can then call them as the oligosaccharides. Or in another way that we use the word oligosaccharide is like when we eat or digest the polysaccharide into shorter chain, but it's not completely digested into monosaccharides. So we call that kind of short chains polysaccharides as oligosaccharides to be avoid the ambiguous about the oligo and polysaccharides, okay, things like that. So in order to understand all of this carbohydrate structure, we have to understand the subunit, the building block, basic building block of the carbohydrate first. So let's start with the monosaccharide. Monosaccharide is the smallest building block, as I said. Okay, we can then again divide the monosaccharide into several types. Okay, it depends on how we identify and how we categorize them. So first of all, because we are chemists, so what we have to look at is the structure, is the functional groups and everything. So monosaccharide can be divided into 2 major subunits. The first major types. The first one is called aldose, and the second one is called ketose. So as you know, almost every carbohydrate end their names with OSE, like glucose, maltose, lactose, fructose, sucrose, things like that. So if your sugar have aldehyde functional group in the structure, we call this kind of monosaccharides as aldose. And also, if you have ketose, if you have ketone, so we call them as ketose. So basically, the aldose sugar is the molecules with aldehyde group. But not only the aldehyde group, is also have another functional groups. So aldose sugar is technically called as polyhydroxyaldehyde from the structure, okay? Because it's a long chain aldehyde composed of many hydroxy group on almost every carbon unit in the molecule. So aldose sugar is the polyhydroxyaldehyde. So obviously ketose sugar is the polyhydroxyketone. So the structure is very simple. Because polyhydroxyaldehyde, for example, you have aldehyde unit like this, and then with many carbons on the right as a tail, right? So almost every carbon, basically conventional carbohydrates, every carbon contains one OH group, like this. Okay? So let's say if we're starting from 3 carbon in the molecules, so we have aldehyde on the first carbon, but the rest carbons in the structure contains OH. Okay? So we may have more than 3 units, 3 carbon atoms. So I will put the N here, okay, to say that whether you have 4, 5, 6, 7 carbon, all of them contains OH. This is just a conventional monosaccharide structure. Okay? But in some cases, okay, we have also other functionalities in the molecules, or maybe some of the carbon lost its O from the structure. Sometimes it happens. Okay, we'll see some kind of examples afterwards. Then we have ketone or polyhydroxy ketone. The polyhydroxy ketone, that means we're starting from the ketone, the carbonyl group. Okay, and we have several carbon in molecules like this. For example, this is tetrose sugar, or we have 4 carbon atoms in the molecule. So we have the second carbon with carbonyl group. So other carbon atoms contains OH. So normally every carbon rather than the carbonyl group contains OH group. So we call them as polyhydroxy because we have many hydroxy groups. Right? We call polyhydroxyaldehyde and polyhydroxy ketone. So this is, we divide them by the functionalities in the molecule, but we can also divide them by the number of carbon in the molecule as well. So we have like 3 carbon in the molecule. We call this as triose sugar. Okay. If we have 4 carbons in the molecule, we call this as tetrose sugar. Right. Tri is 3, tetra is 4, right? So we have triose, tetrose. So if we have 5 carbon in the molecules, we call them as pentose sugar. And if we have 6 carbon in the molecule, we call it as hexose sugar. Okay. But rarely we have 7 carbon, 8 carbon, or 9 carbon, but yeah, just maybe 3 or 5, 4 or 5 kind of higher number of carbon here. In nature, we see hexose sugar, okay, as the most abundant kind of carbohydrates. Okay, why? Maybe because in the biosphere, in our environment, okay, the first type of monosaccharide, the first type of carbohydrates produced in the biosphere on our Earth is the glucose, okay, and the glucose is hexose sugar. So after plants produce the glucose by kind of photosynthesis pathway, and then maybe human, maybe other animals eat the plant and digest it. So we can see the shorter chain of hydrocarbon of the carbohydrates, but no longer chain. Right? So longer chain of polyhydroxy ketone or aldehydes can be rarely seen in the nature. So because we start from hexose and digest it to something smaller. Okay, now. So because we know that we can categorize them by 2 criteria, the functionalities and the number of carbon atom. Okay? So let's start with an example of carbohydrate. Okay? A very famous example of carbohydrate is glucose. So I shall draw the structure of glucose here. Glucose composed of 6 carbon in one molecule. Okay? And as you can see, every carbon contains OH. And this is the structure of the glucose. You may notice that the bonding I draw here, I show you the direction of OH, whether it's pointing upwards from the whiteboard or pointing downwards into the whiteboard. So we have 3-dimensional structure indicating that we have stereoisomer of the glucose as well. But this is the glucose, the most abundant carbohydrates in the nature. Okay. So if you count the number of carbon here, you can see that 1, 2, 3, 4, 5, 6. We have 6 carbon in the molecule with the functionalities of the aldehyde. So glucose is a kind of aldose sugar because it is the aldose with 6 carbon in the molecule. Okay, now, so this is the aldose sugar, the glucose. But anyway, the aldose is not only glucose. We have several aldose sugar rather than glucose. So I will go deeper in details about the structure of the glucose and other form of the sugar, the monosaccharides. Okay, let's see what we have. Okay, we start the monosaccharide with the glucose, the natural abundant, the most abundant monosaccharide in the nature, because this is produced by photosynthesis of every plant in the world. The glucose, as I draw here, showing you the direction of OH, whether it is pointing upward, downward. Okay, and yeah, as you know from stereochemistry, that there are several other probabilities of the structure like this, like the aldohexose, but OH pointing upward and downward different from this glucose structure. But from this picture that I'm trying to draw the three-dimensional structure into this two-dimension whiteboard, right? But how can it be if I just show you into three-dimensional model? So this is the model of glucose. Okay, it's like this. So it's exactly the same as the thing that I have drawn on the board here, as you can see, starting from the aldehyde up there. Okay, the second carbon we have O pointing upwards. Actually, it is OH, but I'm just cut the hydrogen out, okay, to make it simpler. Third carbon OH pointing upward, the third carbon pointing upward, and the fourth carbon OH pointing downward. Okay. And the last carbon number 6 here, OH is here. Actually, the last carbon you can rotate the OH around. The first carbon as well, you can rotate the aldehyde around. You can draw it like double bond pointing downward and hydrogen atom pointing upward. It's exactly the same because this is kind of trigonoplanar structure, right? So they have no three-dimensional structure of that first carbon. The second carbon, OH, is pointing up front. Okay? If you want to point this O down here, you have to break the bond and swap the place with hydrogen atom. So that means if you just swap this O with the hydrogen down here, you have a new kind of molecules, a new kind of monosaccharide, and the name is changed from glucose to something else completely. What I want to show you, for example here, is another kind of aldohexose that you're very familiar with the name. The thing is, I will swap the place of the third OH or the OH on the fourth carbon from pointing upward to pointing downward. Okay. The name is changed from glucose. This is called galactose. So what is the relationship between glucose and galactose? As you can see, we have actually 4 chiral center or 4 chiral carbon. So in total possibility, we have 2 with the power of 4 or 16 kind of aldohexose sugar possible. Okay, this is the first one that I introduced to you. This is the second one, right? But there are other possibilities as well. As I say, from 16 possibilities, right? I just wrote just 2. So all of these, like glucose and galactose, these are the relationship between these 2 isomers is called diastereomer. Because these 2 are stereoisomer, but it's not complete the mirror image of themselves. It is the mirror image on just the carbon number 4. So instead of calling this as enantiomer, right, we call this as diastereomer. What is the enantiomer of the glucose? I will talk about it later, but first of all, when you draw the structure of aldohexose sugar like this, you have to draw it in kind of zigzag structure with the way OH pointing upward and downward was symbolized with the bolded line and the dashed line here. To make it more simple, there are another way of drawing these saccharides, okay, which is called Fischer projection. Fischer's projection. So it's simple. Simply project the picture of three-dimensional picture onto two-dimensional whiteboard here. So how can we do it? Let I show you the very simple structure of kind of chiral molecules. So for example, if we have this, if you have this molecule, okay, so from the glucose like this, I will just cut the rest of the molecules, okay, and then substitute that with R. So I will use one atom as R. แป๊บหนึ่งนะหยิบก่อน So I will symbolize the R group with the blue dot here. Okay, so it is like this. Okay, now from the picture here, I will just turn the molecules a bit into this direction. Okay, and from this direction, as you can see, it's like a kind of cross. Okay? It's a kind of cross by the horizontal line of the cross pointing towards yourself, and the vertical line of the cross pointing outward from you, right? So in this kind of structure, we can redraw it with the central carbon here, right? And then from this picture, I just turn it up. So as you can see, you have the cross. Okay. The horizontal line point out toward yourself, and the vertical line point downward. So what we can see here is the OH is on the right, H is on the left, R group pointing downward, and then the carbonyl group is pointing upward. The carbonyl group here, you can draw it, carbonyl double bond O on your left hand, hydrogen on your right hand, or you can just turn it, carbonyl on the left hand and hydrogen on the right hand. But what you cannot do is swap the place between C and H, because if you swap the place between C and H, you have to break the bond. But if you don't break the bond, you have to turn like this. But now it's not like this, right? It is on the opposite way. The horizontal line, instead of pointing upward, is pointing downward, and the vertical line, instead of pointing downward, is pointing upward. But we have a negotiation here for the Fischer projection. Fischer projection says that if you want to draw the cross like this, the horizontal line have to pointing toward yourself always, and the vertical line pointing outward always. Okay. So from this criteria, we can then project the three-dimensional structure into two-dimensional structure by just cross it. So without bolded line and dashed line, okay, we just cross like this. So this is kind of rules of the Fischer projections drawing, that the cross composed of horizontal line pointing upward and vertical line pointing downward. So we can draw it like this. And everyone in the world will know that H and OH is pointing outward and aldehyde and R group is pointing downward. Okay? This is the rules of how you can draw the Fischer projection. So from this structure, if you have a mirror in front of it, the mirror image on top here, you will have something opposite with the structure by swap the place between OH and H. Now your H atom pointing outwards and OH is pointing inward to the board. And again, because you just swap the place between your O and your H, right? So you have H pointing up and O pointing down, like this. And again, we want to draw it in Fischer projection, right? So we turn it out up like this. So what you can see is OH and hydrogen swap the place already. And aldehyde in the same place, R group in the same place. So what you can draw here is like this. CHO on top, R group downward, hydrogen on the right, and your OH is on the left. And again, you can cross it to be Fischer projection by the rules that horizontal line pointing upward and vertical line pointing downward. So you have this, CHO, R, OH, and H. So this is the Fischer projection. So again, from the glucose, you may draw the Fischer projections of the glucose as well. Okay. Now, let's see what happens if we want to draw the Fischer projection of the glucose. So now we come back with a glucose model. Okay. As you can see from the three-dimensional structure, which is symbolized by our zigzag structure line, like that. Now we're going to change that line structure to the Fischer projection. So we have to follow the rules of Fischer projection that the horizontal line pointing upward and vertical line pointing downward. Okay. But now we have several carbon atoms. It's not like this, we have only one carbon atom. But now we have several carbon atoms actually. So what happens is we have to align all the carbon lines, okay, into vertical fashion. So what we can do it in two ways. First of all, the aldehyde on top, okay, and drag all the thing downward. Or we can put the aldehyde at the bottom, okay, at the line, roll upward like this. So there are two ways, right? But the Fischer projections, again, we have another rules that the aldehyde, because actually the long chain hydrocarbon here, the long chain of the molecules here, we have two ends, okay, the aldehydes and the alcohol at the very end here on the right hand. So the priorities by priority rules, exactly the same rules that you have to use to identify enantiomer. This carbon contains two O and one H. But this carbon contains one O but two H. So 2O, 1H has higher priority. So the higher priorities, we put it on top and drag down under with the least priority. Okay. So by Fischer projection, I will draw it with the aldehyde on top. And carbon number 1, 2, 3, 4, 5, 6. No? So we have all 6 carbon. Then we just arrange themselves downwards. So first of all, the aldehyde is on top. And we have several carbon runs down, okay, vertically. So now, it's out of space. I have to erase something. Okay, so from this, okay, the first carbon, second carbon, third carbon, fourth carbon, fifth carbon, and sixth carbon align downward. So it's in each intersection is like this. Right? So each intersection contains one carbon atom. Okay, so we have 1, 2, 3, 4, 5, and 6. Carbon number 6 is this one. Right? As you can see, carbon number 6 is a chiral. You have no stereogenic center, right? This is not the stereogenic center because you have 2 of the hydrogen atom together like this. So it can move, it can rotate in any direction, right? So that means the OH of the last carbon is no meaning. You can draw it right, left, down, whatever. So because it is no chiral center, it's not the chiral center. So we don't have to use Fischer projection for this carbon atom and also for this carbon atom, right? Because this carbon atom is not the stereogenic center. So the rest 1, 2, 3, 4 carbon atoms are stereogenic centers, so we need the cross. Okay. And again, because of the rules, right, when you want to draw the Fischer projection, the vertical line have to stay away from you, and the horizontal line go toward yourself. So this second carbon, as you can see from this line, the second carbon contains OH and H. The OH is on the right hand. So we just draw it, OH on the right. Now go further downward to the third OH. Because when we start, we're starting from this zigzag structure. But now we put it upward, okay, and because we have to turn it like this, OH on the right. The third carbon is not OH on the right, because the third carbon here, as you can see, the vertical line pointing toward yourself and the horizontal line pointing outward is against the rules. So you have to turn it a bit, like this. Right? Now, as you can see, the third carbon, vertical line pointing outward and horizontal line pointing toward yourself. And the O will be on your left hand. So for the third carbon, OH is on the left. H is on the right. Now to the fourth carbon, you have to turn it a bit, again 180 degree, right? To let the vertical line pointing outwards and horizontal line pointing toward yourself, and then your OH will be on the right. And again, with the carbon number 5, turn it 180 degree again. As you can see, vertical line toward yourself, vertical line outwards and horizontal line inward. OH will be on your right. So from this glucose, you change it to be Fischer projection like this. So Fischer projection is actually the vertical line pointing outward at every carbon atom, at every stereogenic center. So actually from this zigzag structure, you have to turn it up, and then you better turn every vertical line pointing outward from yourself. So it will be something like this, okay? And then from this, we have to force it up, oops, like this. So this is the Fischer projection of your compound, of your glucose. So as you can see, if I trying to make every single carbon atoms in the vertical line pointing outward, your glucose molecule is curved back like this. Right? It's by the rules of Fischer projections. Right? So it's different from this, zigzag pointing up, down, up, down, up, down, but this is pointing into the same direction, right? And curve the molecules to the back. Okay? This is the Fischer projection of your glucose. Now, what else? The glucose here is the first monosaccharide produced by photosynthesis, and it's the most abundant carbohydrate in the nature. After the photosynthesis in the chlorophyll, making this compound. Okay. Afterwards, some plants gonna change the structure of glucose to something else. Okay. So let's say if it swap the OH here from right to left. So instead of right, left, right, right, it will be right, left, left, and right. Okay. So the name changed to be galactose, as I already talked about it before. Or if I change the first OH here to the left, the name changed to be mannose sugar. So there are several possibilities, exactly 16 possibilities. So we have 16 different stereoisomers of the glucose. Okay. So anyway, by chemical reactions to swap the place between H and OH, okay, in the plants or in animals, in any kind of cells, we use catalyst, which is actually called enzyme, in order to change the structure. So the enzyme gonna trap the molecules doing chemical reactions like digestion from 6 carbon to 5 carbon. So when the cells going to digest your glucose is trap the molecules and then cut from top to bottom. So we have smaller molecules of monosaccharides, from hexose to bipentose, tetrose, and triose. The smallest compound, which can be categorized as carbohydrates, have to contain at least 3 carbons. So we have monosaccharides starting from 3 carbons, okay, triose, tetrose, pentose, and hexose. And as I say, because of the enzyme things. And you may know from your high school that the enzyme, when it in their reactions, there are 2 parts of the enzyme structure. The first one is called binding site, which binds to the molecules. Secondly, you have active site, which reacts with the substrate, reacts with your molecules. So apparently, the binding site is somewhere around here. So what we can see is that from glucose by photosynthesis, the chemical reaction takes place on the glucose. You can arrange the structure of the glucose, just only the top part. But in nature, the bottom part is stay like this, never changed. So the last OH stay on the right always. Okay. In nature, every monosaccharide contains this OH on right hand only. Okay. So enzyme may switch the OH from here to the left and creating the galactose. Switch this OH to the left and produce mannose. But they never switch the OH here to the left. So this glucose, this saccharides contain OH on the right. The last stereogenic center pointing OH on the right is called D isomer. D stands for dextro, which means right hand. The opposite stereoisomer of this is called L, or levo. Levo is left. D is dextro. So in nature, I would say that this is the natural abundant. Sugar. And this is rare sugar. So we rarely see this kind of levo isomer. Okay. So the full name of the glucose with this Fischer projection structure is called D-glucose. So as you know, we have enantiomer, right? So if you have a kind of mirror here, then we have a mirror image of the glucose on the right. And the mirror image of the glucose can be drawn like this. So you swap OH and H from the natural abundant glucose or D-glucose to be something opposite, this one. So this is called L-glucose. And this is rare sugar. Okay. In nature, we have only D-glucose, not L-glucose. So that means in your body, the enzyme in your body is designed to capture the glucose and drag it down to glycolysis, producing energy for you, for your cells. And because the enzyme trapped the glucose with the binding site around here, so we rarely see this kind of thing. So the enzyme designed to trap this one, not this one. So if you can synthesize the L-glucose and you just eat it up, right? No enzyme in your body recognize this one, recognize this molecule. So this can pass your metabolism's pathway. So nothing can catch it. So this is eliminated from your body with the urea and everything. Okay? So we can just test the sweetness of this L-glucose, but we can never digest it. So this is very suitable for some patient with glaucoma, things like that, because the body cannot recognize this one and get rid of it in the aqueous media with the urine, thing like that. Okay, no? So this is the Fischer projection of the glucose. Another example of monosaccharide is derived from the glucose here. So you may notice the name fructose. Okay. Fructose is another product of photosynthesis. So actually after photosynthesis, the glucose is isomerized to be fructose. So isomerized means that the way of bonding is changed, but the number of carbon, hydrogen and oxygen are still the same. So fructose is the way the cells just reduce carbonyl here and oxidize this carbonyl. Or we can say that it swap the place of the carbonyl group, the double bond, C double bond O, from the first carbon to the second carbon. So what happened after that is the first carbon is reduced to be CH2OH, and the second carbon is oxidized to be double bond O. But this double bond O is trigonoplanar, as you may know. So that means you can draw the double bond O from pointing toward the left hand or right hand is exactly the same, because it's like trigonoplanar, right? So you can swap it. You can rotate the molecules very easy. Now, other carbon atoms are exactly the same. So it's on left and it's on right and right again, and ended with CH2OH. So this is the fructose, and as you can see that the OH is still here because the enzyme that isomerizes the glucose to be fructose, it traps the molecules here with the active sites, reacts the molecules on top and change the double bond from C double bond O on the very first carbon atom to the second carbon atom like this. So the name of this is D, fructose. Okay. And we can also draw the fructose in the same fashion as the zigzag structure of the glucose. So in fructose, it is like this. The first carbon is CH2OH, the second carbon is carbonyl, third carbon, fourth carbon, and fifth carbon, and sixth carbon, 1, 2, 3, 4, 5, 6. The sixth carbon is non-stereogenic center. So you can draw OH in any direction, but the rest is dependent, right? So this is the third carbon here. As you can see, it's pointing OH on the left hand. So from here, because when you draw the Fischer projection, the vertical line pointing outward and horizontal line pointing downward. So it is like you laying down here, looking up to the molecules. As you can see, your head is on this way and your feet is on this way. So if you lay down here and look up, you will see OH on the left and H on the right. That means the OH is pointing downward and H pointing upward. So I can draw it like this. Now, the fourth carbon over here, it's like you have to lay down here and look down onto the molecule. So if you look down to the molecules, OH and H is pointing towards yourself, right? And the way that OH align is on the right hand. So with OH on the right hand, in this picture, that means the OH is inside and H is outside. So when you turn up, your OH is on the right hand. Okay. And the same with the last number, last carbon here, the last stereogenic center carbon, and number 5, OH is on the right. That means the OH is upward. Okay. You can check the structure by S&R configuration of your enantiomeric things in the previous chapter as well. Anyway, this is fructose, and to be clear, this is D, fructose. Okay, so roughly this is the kind of Fischer projections of the monosaccharide. So after we know the structure of the monosaccharide, now we're going to look at the reactions of the monosaccharide. Okay, so after we know about the structure of monosaccharides, now we're going to look at the chemical properties or chemical reactions of the monosaccharide. And of course, the chemical reactions here will lead to the higher order of the saccharides to be disaccharide, polysaccharide afterward. Now let's begin with the very first reaction, the cyclization. And then we're going to look at the oxidation, which is very important reactions from the saccharide as well. And then we ended with the glycoside formation, which is the way we construct higher order or bigger molecules of carbohydrates. So let's start with the first reaction, cyclization. So cyclization is a way that the glucose or other monosaccharides can cyclize itself into cyclic structure. As you may notice in your high school, that in biology they normally draw the glucose structure in 6-membered ring in hexagonal structure, and also the fructose they normally draw it into 5-membered ring or pentagon like that. So what is behind the cyclization reactions, how it can happen? Let's look at the basic chemical reactions of this kind of thing. So first, cyclization. So this is actually in equilibrium. The glucose molecules or any other monosaccharides can close itself into the ring structure and then open it again back to the Fischer projection open chain structure. The reaction here is actually called as the nucleophilic addition of carbonyl. So the requirement for the reaction, you need 2 functional groups, aldehyde or ketone, let's say carbonyl group, and the OH. Okay? So the reaction is like this. You're starting from aldehyde or maybe ketones. It depends on H or R, right? And then you will condense it with alcohol, like this. As you can see from the chemical structure, carbonyl group, oxygen with very high En number can withdraw electron from the carbon center here and make your carbon center slightly positively charged. And the oxygen here is slightly negative. So we have positive and negative in the molecules. And as a result, you have electrostatic attractive force with other molecules over here. So as you can see, we have O, which is electron rich, right? So this O, which electron rich, will react with the carbon here, which is positive, partial positive, because of the E end of oxygen withdraw the electron from this carbon up. So negative and positive reacts with each other. So what happened is, your R group, okay, you have H or maybe R, depends on aldehyde or ketones. Now your oxygen reacts with this one. So what happened is, I would label this oxygen with blue color. So this oxygen reacts with the C, right? So you connect O and C together, okay? And then GO is bounded with R group. So this is your R group, okay? But because the oxygen can bear up to just 2 single bonds, right? Now you're creating another bond over here. So it will make the oxygen overoctet. So what you have to do is release 1 bond out of the molecules. So I will just kick this H out. So I will label this H with the bolded line, okay, this bolded H. So this one is released from your alcohol. And where it can go, as you can see, the double bond of the carbon is broken down because carbon can bear up to 4 chemical bonding, right? If you construct the 5th chemical bonding, it's impossible. You have to release this pi bond, right? Pi bond is weaker than sigma bond, as you know. So pi bond is released up. So your oxygen here, instead of 2 electron pair, now you have the 3rd electron pair, okay, which is come up from the pi bond, from the broken of the pi bond. So oxygen is negative now, but you have H release from the alcohol. So at the end, that H is recombined with the O up here. So you have this. So actually, it's a kind of reactions that you opened the double bond, the pi bond between C and O. Okay? C, which is positive, will bind with the O, which is slightly negative. And the O with negative charge will bind with H, which is positive, right? So you can just add up H and O into the double bond, okay, and end up with this. Right? This is called addition of the aldehyde or of the ketone by the alcohol. So now, if we talk about glucose or fructose or galactose or any other monosaccharide, the monosaccharide, you have H or R, depends on aldehyde or ketones. And from your Fischer projection, you have several O in the structure. So one of the O in the structure can then react intermolecularly with the carbonyl. So at the end, you're creating this kind of structure. The O is then knocked down onto your carbon atom, and then you lost this H, okay, to preserve the 2 bonds of oxygen. Right? You lost this H, and that H will connect to the O, which previously bind with the carbon with double bond. Now you have only single bond left here. H and R is still here. Okay. So this is cyclisation. And as I said, actually this reaction is in equilibrium. So the cyclisation, the ring closure and ring opening is in equilibrium as well. So you have to select one of the O in the structure to condense with the carbonyl and end up with the cyclic structure here. Okay. So cyclic structure can be triangle, square, can be pentagon, can be hexagon, can be anything. But the stable cyclic structure here have to be 5 to 6 membered ring. So you may end up with pentagon or hexagon only, no other size of cyclic structure can be seen in the nature. They predominated with 5-membered and 6-membered ring. Okay, just that. This is why we draw the structure of glucose in hexagon and the structure of fructose in pentagon. Okay, so that's it. This is a cyclisation. Right? So if we look at the glucose, for example, you have OH on every carbon atom, like this. So it can actually close the ring into both sides, 5 and 6 membered ring. And because it is in the equilibrium, right, you also have the open chain structure here as well. But because the equilibrium prefer, the most abundant structure observed from this equilibrium is the form, is a structure with the lowest energy states. Okay, but because you are in just first year student, you cannot know exactly which kind of structure is the most stable form between open chain 5-membered ring or 6-membered ring. Okay, you don't have to know exactly what is the most stable form here. I just want you to see that in your high school biology, right, you can draw it in both open chain structure or in this cyclic structure. Another thing that I want you to know is that when you knock the O with carbon here, creating this cyclic structure, you also produce this chiral center. This carbon contains 4 different single bonds, right? So this is the chiral center. So that means from aldohexose with 4 chiral center, after you lock it into cyclic structure, you're creating another chiral center over here, right? Because this is a chiral, but after you knock it down, you change this achiral carbonyl into chiral carbon. That means instead of 16 possibilities in cyclic structure, you're creating another chiral center. So you double the possibilities to be 32 possible structures, or 32 possible stereoisomers, okay, in 6 members. And also in 5 members, you also construct another 32 possibilities. So there are kind of mixture of things, okay, in the saccharide chemistry. Okay, I will not close the ring for you. Okay, I will not show you how to close the ring, but I want you just to know that it can happen. Okay, and that's enough. Another thing that I want to show is, as you can see from the structure over here, every carbon contains 1 oxygen atom, bound to 1 oxygen atom only. And more specifically, the first carbon atom bound to 1 oxygen atom again, but with the double bond. But after you cyclize the system up, as you can see, the carbon here contains 2 oxygen atoms. Right? This O is previously appeared as the double bond, but now it's left only 1 bond, right? The single bond, because the pi bond is broken down by this condensation. So this carbon is previously appeared as the carbonyl group. I want you to find this kind of carbon because it is very important for other reactions afterwards. Okay. Anyway, I will show you the structure of glucose after cyclization. The thing that you may be familiar with in your high school is like this. Okay. At the very end, the structure of the glucose in hexagon kind of thing is like this. Okay. So this is also the glucose. So what is how relate the structure of this one and this one together? First of all, as I said, the O here containing 2 oxygen atoms is previously appeared as a double bond. And as you can see from the structure over here, that this carbon contains 2 O. Okay. So that means this carbon is previously appeared as the carbonyl over here. So if this carbon is labeled number 1, 2, 3, 4, 5, and 6, this carbon is the carbon number 1, which is previously appeared as the carbonyl group. And as you can see, that the carbonyl group was condensed already with its oxygen. So this oxygen in the ring is the oxygen that is used to condense with the carbonyl. So it is this one. Back to the left-hand side structure. Carbon number 1 is over here. So it connects with another carbon number 2, number 3, number 4, number 5, and number 6. 1, 2, 3, 4, 5, 6 along the line here. Okay. So as you can see, that the pink oxygen is the oxygen belong to the carbon number 5. That means this oxygen is used to condense with the carbonyl and creating the 6-membered ring structure of the glucose. Like this. Okay. So what I want you to know is, if you look at the structure of glucose or any kind of monosaccharide, you have to firstly find where is the carbonyl. Okay. The carbonyl is now hidden in the ring by the condensation of the oxygen. You have to find it. And you, from this structure, you know exactly this is aldehyde, this is aldose sugar. But from this, you cannot see whether this is aldose or ketose, right? But it's clearly see actually, because aldehyde contains H, but ketones contain R here, right? So after you find where's the carbon number 1 here. Where is the carbonyl? Look at this. Your carbonyl connect with carbon and hydrogen, right? So that means carbonyl with carbon and hydrogen is the aldehyde, right? But if the carbonyl contains carbon and carbon, that's the ketones. So if you can see the H here connect with the carbonyl, that means this H, that means your sugar is aldehyde. But if the carbon with 2 oxygen connect with 2 carbon left and right, it means that the previous structure is the ketone. Okay, that's it. This is what I want you to know. And this is the first reaction, the cyclisation. Now we have 2 more reactions to go. So continue to the second reaction, the oxidation. So next reaction is the oxidation. Okay. So there are many kinds of oxidation process can be happened with your carbohydrates. But I will just show you just one type of oxidation process. Okay. It's the easiest one actually. So the oxidation, actually the functional groups that can be oxidized is both aldehyde and hydroxy group. But aldehyde is not very stable. It can be easily oxidized comparing with the OH, which is more stable. And to oxidize the OH, the alcohol to be ketone or something else is very difficult comparing with the oxidation of aldehyde. So if you have aldehyde, you can selectively oxidize it with the OH or hydroxy group untouched. So the aldehyde can be oxidized very easy, as I said. The product of the oxidation of aldehyde normally measure is the carboxylic acid. So if you track the oxidation number of this carbon, as you can see, this carbon is bounded with another carbon with the same En value. So this carbon has no effect with the oxidation number of this carbon. But anyway, this carbon can withdraw electron from H atom here. So it takes 1 electron from H, but it lost 2 electrons to the oxygen by the double bond. So lost 2 electrons and accept 1 more electron. In total, your carbon lost 1 electron. That means the oxidation number of this carbon is +1. So if you look at this carbon atom, it connects with 3 bonds of oxygen atoms. That means this oxygen takes 1 electron from carbon, but this top oxygen takes 2 electrons from your carbon atom. And then the oxidation number of this carbon atom is 3, +3. So this is the oxidation process. So obviously, this can be happen if you have a suitable oxidizing agent. Okay? But if you want to selectively oxidize this aldehyde without reaction with the alcohol, because your monosaccharides contain not only aldehyde, you also have hydroxy group, several hydroxy group in the molecules. So if you don't want to mess up everything, you have to selectively oxidize this only aldehyde group. So you have to use a very weak oxidizing agent. And that oxidizing agent in this reaction that I want to show is the copper-2. Copper-2 sulfate, for example, is in the solution form, aqueous solution in blue color. After oxidation, your copper is reduced, right? Because the oxidation and reduction process happens together. If one of the chemicals take electrons from someone else, that means you oxidize that thing, right? So this copper takes electron from your carbon atom and oxidize it from +1 to +3. So your copper is reduced because it takes negative charge toward itself. So instead of 2+, the oxidation number is reduced. So normally your copper 2+ is precipitated out as copper 1 oxide in red color. And this is called Benedict Test. Right? We actually have Benedict Test, Fehling Test, and also Talent Test that can selectively oxidize your aldehyde to be ketone. But I show you just only this reagent, copper-2 iron. Okay. So this reaction takes place in the basic solution. You can use several kinds of base, but not sodium hydroxide, because sodium hydroxide will react directly with the copper ion, creating copper hydroxide instead. So the base over here, we normally use the kind of salt of carboxylic acid. Okay, and you also need heating as well. So this is the oxidation of the aldehyde. But more specifically, if you have ketone is normally inert to the oxidation. But the hydroxy ketone, this is called alpha hydroxy ketone because the OH is connected with the alpha carbon. Okay? The carbon connected adjacent to the carbonyl group is called alpha carbon. So this alpha carbon connected with OH. So this is called alpha hydroxy ketone. Alpha hydroxy ketone can be oxidized with the same process, but the product is like this. You end up with diketone instead. Okay, so this is the oxidation. But in your monosaccharide, as I said, for glucose, for example, your glucose, you have kind of this Fischer open chain structure. But the glucose can also, in equilibrium, can also cyclize to be 6-membered ring, or can be also 5-membered ring, or anything. So it's like this. Okay. So in form of this cyclic structure, this is aldehyde, no? Or maybe it can be ketone, but I just show you aldehyde form. This aldose sugar cyclized to be something like this. But this structure, you cannot see the aldehyde. That means this structure is inert to the oxidation process. Okay, this is the inert chemical form of the monosaccharide. But anyway, you have equilibrium between the two. For example, the glucose, actually in equilibrium, the glucose prefer 6-membered structure. It takes about 60–90% of the 6-membered structure. 5-membered is minority, and also the open chain structure here is very minor in the mixture. I cannot remember exactly what is the percentage of this one, but it's very low. So if you want to oxidize the glucose with the copper ion in the Benedict test, what happens is it can oxidize only the open chain form, which is very minority in the process. But you know the what is called Le Chatelier, right? When you in your high school, no, you learned Le Chatelier principle. So if this one is oxidized, that means you get rid of this one. Right? So the equilibrium shifts back to the open chain structure. So if this is oxidized out, then the cyclic structure is open out to be open chain like this, and it's oxidized. So eventually, the whole mixture was completely oxidized by the Benedict test, right? Because after the open chain, the aldehyde is oxidized, then you get rid of this one, the equilibrium shift back by Le Chatelier principle. So this is the oxidation process. It can happen with the aldehyde and with the ketose sugar as well, but by these lines. Okay, oxidize the ketose sugar to be diketone structure. Now we come to the last reaction, glycoside formation. Okay, now we come to the last chemical reaction for your monosaccharides, the glycoside formation. The glycoside formation is very important because it's going to construct a higher order of saccharides like disaccharide, trisaccharide, and many other things. Okay. So for glycoside formation, I would starting from the aldose sugar, one of the aldose sugar. So this is aldohexose, and I just don't want to mention about the sterol center. Okay. So I just put OH without direction, pointing upward and downward or anything, without the configuration. So if this oxygen condenses with this carbon, you can then construct 1, 2, 3, 4, 5 and 6 membered ring. Okay. You can construct the hexagon out of this. So in equilibrium, you will have this one. So the oxygen over here in pink color is that oxygen. With the cyclisation, you connect that pink bond to the carbonyl. So the carbonyl over here is changed to be single bond, right? From the double bond O, you have single bond O. That's the first carbon. The second carbon contains one OH, the third carbon, the fourth carbon, and the fifth carbon with OH is like this. It now connects with another carbon number 6 and then OH. So this is the hexagon structure. So after cyclize, as you can see, the first carbon or the carbonyl group is here. As I mentioned earlier, that the carbonyl group is now connected with 2 oxygen atoms. The previous one is this one, is the carbonyl, right? And then we have hydroxyl group condensed to it. You have something like that. Another example that I want to show is the fructose. So if I symbolize the fructose over here as the kind of ketohexose sugar, but without mention of the configuration SNR isomer, we have this one. So you know that fructose in your high school always draw in 5-membered ring, thing like that. But actually fructose can close in 6-membered ring as well. But the majority of the fructose in equilibrium is a 5-membered ring. So if this is the first corner, then the second corner, third corner, fourth corner, and the fifth corner going to be oxygen over here. So in similar way, you can now construct 5-membered ring. And from your high school, you may familiar with the structure of 5-membered ring fructose like this. So again, the oxygen, pink oxygen, reacts with the carbonyl, like this. And now the carbonyl double bond is released to be single bond. This is OH, okay, of that one. Okay. I would label the carbonyl oxygen with blue color, so you can track back easier. Okay. And then we have first carbon here, right? So don't forget about that. And then second carbon is the carbonyl. The third carbon contains one OH. The fourth carbon also one OH. The fifth carbon, you use this oxygen in order to condense and cyclize the structure. Sixth carbon with OH over here. So now if you want to track back, you can see that this carbonyl is here. As I mentioned earlier again, the carbonyl is now changed to be something else, connect with 2 oxygen atoms. So when you see the cyclic structure, what you have to find first is the oxygen connecting with 2 oxygen, is the carbon connecting with 2 oxygen atoms. And then you can know automatically that this one is previously appeared as the carbonyl. So this one is appeared as the carbonyl previously because this one is connected with 2 oxygen atoms. And with this carbon, as you can see, it connects with 2 more carbon atoms. So if this is previously appeared as the carbonyl, these 2 carbon identified as the ketones. But this one, you have only 1 carbon left, right? So we hide 1 hydrogen atom in the line structure. So actually this is aldehyde. Now, every OH can act as a hydroxyl group. So it reacts exactly the same with other kind of alcohols. For example, it can react with the sodium metal, releasing or liberates hydrogen gas as a product, for example. Or you can use these alcohols to condense with the carboxylic acid, and then you have ester as a product. So it's conventional alcohol, reacts exactly the same as other alcohols' functionalities. But one of the reactions that is very unique for the sugar is this OH and this OH, which is actually previously appeared as the carbonyl group, is the most reactive OH in the structure. But why this 2 is the most active or active functionalities in the structure? There are reasons behind it, but you have to study the organic chemical reaction mechanism first in the second year, sophomore. So now, you may just have to remember that these 2 OH, the OH that is previously appeared as the carbonyl, is the most reactive one. And these kind of OH, I will symbolize them as this. Okay? Labeled in OH and labeled the hydroxy group that's used for condensation in pink color. Okay. So it can be aldehyde or it can be ketone. This OH is the same thing, right? It's the most active one. The reactions, the glycoside formation, is when you have the cyclic structure of sugar. This OH can be substituted with something negative charge. Okay? Let's say if you have X group with electron pair, okay? What happens is this carbon is very positive because you have 2 oxygen attached onto this carbon and make this carbon very, very positive because oxygen has very high En value. So if you have 2 oxygen atoms, very high En value of both oxygen atoms can withdraw electron from your carbon here and make this carbon very reactive, very positive. So this carbon can react with a negative thing, like X group. So X group will substitute something here in the structure. And a very easy way is you just kick out this O as the hydroxy group, as a leaving group. Okay? So as a result, the product from this kind of substitution, okay, the product from this kind of substitution, everything is exactly the same except the OH over here is substituted with the X. You have X here inside as the product. So OH is released as a hydroxide, for example. So this kind of thing is called glycoside. For example, you may heard the word glycoproteins. So glycoproteins is you use proteins to react with your sugar, and at the end you have proteins connecting with the sugar, and we call this as glycoproteins. Or glycolipid is quite the same, right? You have lipid reacts with the glucose or monosaccharides, and at the end you have the combination of lipids with the sugar, and we call this as glycolipid. Okay? So glycoside is the compound that was substituted, the first OH, or the OH that was previously appeared as the carbonyl group, was released and substituted with something like this. It can be any kind of molecules with negative charge or with very high density electron pair like this. I will show you one example for this. So, for example, if you have a glucose, and if you have another glucose on the left hand and on the right hand, and let them condense together. So actually, we have several OH and several electron pairs in the system. So this kind of condensation is controlled by an enzyme. So it depends on what kind of enzyme used in the chemical reactions in your biological system. So let's say that if you have a glucose over here, if you have another glucose over here, and the enzyme of a plant is used to condense these two glucose together, by electron pair of the oxygen over here is controlled by the enzyme using this electron pair to substitute and kick out this OH. So at the end, the product is like this. This is the left hand glucose unit. It is now condensed with this one. So the OH of the previously appeared as a carbonyl is kicked out, right? The O over here condensed. So you're constructing this bond. You have oxygen of the second glucose unit condensed with the first one. Okay. So this is the product from the condensation. And actually, you can use other oxygens to condense with this one as well, right? So if you use other oxygen atoms, you have different kind of product with different names, okay? So there are many possibilities to condense two glucose units together, or condense any other of monosaccharides together, creating several thousand or countless number of the product, okay? So, as you can see from here, normally the glucose structure or monosaccharide structure is in equilibrium with the open chain and closed chain or cyclic structure. So now again, your molecules is in the equilibrium as well. So as you can see, this is OH, right? OH is dissociated very easy, right? It's like water. You have dissociation constant of the water as 10 to minus 14, thing like that. So OH here dissociated and then reverse back to the open chain structure. So you lost this OH, okay? I will draw the right hand ring first. So after it is released out, okay, what you have is the oxygen over here. Come back, okay? Instead of hydroxyl group, okay, you release it back to the open chain structure as an aldehyde over here. So this is in equilibrium, right? You have to get rid of this H, okay, and return back the double bond, okay, and cleave this CO bond back to OH. So this is the open chain structure, okay, and this is the cross chain structure, cyclic structure. But if you look at the left hand unit, okay, oxygen over here has no hydrogen, right? Because it is now condensed, no? So to open the chain back to the open chain structure, you have to dissociate this H, right? And then you have double bond back. But this is CO bond, which is very strong. You cannot cleave the CO bond very easy. So if you cannot cleave the CO bond, that means this one is stay like this forever. You cannot open the left hand ring. You can open only the right hand ring, like that. So if you can open only just the right hand ring, So you have aldehyde back here, right? But it's in the equilibrium, right? And in the equilibrium, normally it's preferred the close link. Anyway, if you treat this kind of thing with the Benedict test, the Benedict reacts with only a carbonyl group, right? With the aldehyde group. So that means the Benedict will react with just on the right hand ring here, because the right hand ring open it like this and reacts with the carbonyl, with the copper ion in Benedict test and shift the equilibrium. So Benedict test cannot react with the left hand, it can react with only the right hand. Okay? So that means if you have a monosaccharide, you have equilibrium of open and closed chain, you can do oxidation with Benedict with this one. But after you make the glycoside out of the monosaccharide, so you don't have the OH left. You put X something inside instead, like this. You put the whole molecules here on top of this, right? So you don't have OH left. You have something else. So without OH dissociation, you cannot open the chain of the left hand. You closed it forever. So that means this is inert to the oxidation process with the Benedict test. So the sugar that can reduce the copper ion, we call this as reducing sugar. We call this as reducing sugar. We call this as reducing sugar, and we call this as reducing sugar. But once you close it forever by making glycoside, you cannot open this chain. You don't have the aldehyde. You don't have the ketone back. So that means this one cannot reduce the copper ion in Benedict test anymore. So this kind of sugar, or the glycoside, is called non-reducing sugar. Okay? So this summarizes all the things in carbohydrates. Now, next video we will discuss about the properties and with chemical reactions, everything, with the actual structure of compounds. So I think there are so many kind of details here in this video. You may have to go back and reconsider everything in this video again, one more time maybe, and then we'll look at the homework that I will show you, and after that we will discuss about the homework in the next video. Before the end of this chapter, I will have 5 structure of saccharides for you to discuss about the properties of the saccharide. So I will show you one of the examples, cellobiose over here. What I want you to do is to classify the type of unit, the monosaccharide unit in each structure, and also trying to find out whether the compound over here can undergo oxidation by Benedict test or not. Okay. So I will show you the cellobiose first, and the rest of the molecules over here we will talk about this kind of thing afterwards in the next video. But I will let you discuss about the structure of this as your homework. Okay. Now, going to look at the cellobiose, there are 2 subunits, left and right. I will look at the left-hand side structure first. First of all, you have to count the number of carbon. So as you can see, we have carbon number 1, number 2, 3, 4, 5, 6. So you have 6 carbon. So obviously, this one is hexose. This one is hexose sugar. And from the structure over here, you have to find the glycosidic carbon, or the carbon that was previously appeared as the carbonyl group. So as you know, the carbon connected with 2 oxygen atoms is this carbon. It's the only carbon in the ring connecting with 2 oxygen atoms. So this carbon is previously appeared as the carbonyl group, but it is closed because this oxygen condensed with that carbonyl. Okay? And then the double bond O is over here, was released from double bond O of the carbonyl to be OH, and then it's condensed with another unit over here on the right hand by glycosidic formation. So if this is the carbonyl group, the carbonyl was once connected with the double bond over here, but then this is carbon, so another bond over here that hide behind it is the H. So that means it is previously appeared as the aldehyde group. So this is the aldohexose. This is the thing that you have to do. Find out the subunit, whether it is aldose, ketose, and how many atoms of carbon in the structure. Now looking on the right hand structure over here, 1, 2, 3, 4, 5, and 6. Okay, no matter how they just flip up and down, okay, to show the tetrahedron structure or anything, you just count the total number of the carbon, then you know that with 6 number of carbon, this ring is also a hexose sugar. And from the hexose sugar over here, again, you have to find whether this is the aldose or ketose. So first of all, you have to find the glycosidic carbon, or the carbon that is suitable to make the glycoside, right? So it's the carbonyl previously appeared as the carbonyl, which is this one. So this is the only carbon atom that composed of 2 oxygen atoms bound to it, right? So this is the hydroxyl group condensed with the carbonyl. So this O was previously appeared as the carbonyl group, right? And so if this is the carbonyl, you have only 1 carbon here, and another bond is hydrogen atom. So this is aldose sugar again. So both of the subunits is aldohexose. And for the right hand ring over here, as you can see, the OH can be released back to be carbonyl by the double bond forming back, okay, and cleave this single bond out attached with the hydrogen, and then you turn back to the carbonyl. So the carbonyl can come back if the glycosidic oxygen is OH, right? So after it turned back, I will draw it for you. So you release the cyclic structure back to open chain aldehyde, right? So because it can open back to the aldehyde functionalities, so this one can react with the Benedict, right? So on the right hand, this is reducing sugar. You can react with the Benedict test. So I will mark this one to say that this is positive, or I would say positive to the Benedict test. But this unit, because you don't have the OH, the oxygen is substituted with the whole ring here. So this is no OH. So there's no way to deprotonate it and forming back the carbonyl. So this ring is closed forever. So it is negative to the Benedict test. So this is non-reducing part, and this is the reducing part. Okay, I want you to do all this kind of thing with the rest of the structures. So you have 4 types of sugar as your homework. So you have to kind of find whether each ring is aldose or ketose, how many carbon atoms inside, and where is your glycosidic carbon, right? And identified whether the ring can be opened or not. If it can be opened out like this, it undergoes oxidation, and it is positive to the Benedict test. But if the ring is closed forever, because the OH is substituted with something else like this, so it is negative to the Benedict test. So this is what I want you to do, okay, as a homework. And that's all for the carbohydrate. So next video, we will make a discussion about the rest of the structure, okay, and we will end the carbohydrates here. Thank you very much.